physics class. Today we're going to start looking at probability, and you'll find that probability and statistics will underlie a lot of what we do for the rest of the semester. This is a slide deck of 45 slides. We will spend several days going through this, and we'll do more things and more examples than are in the slide deck. But today I'm just going to give you an introduction for the basic ideas to set the stage for our class meeting next Monday. So we're going to introduce some basic ideas. So here's a quick summary of all of the topics that we'll cover. We have to do lots of things: introduce probability, introduce a sample space, learn lots of definitions, learn how to combine probabilities. We have to look at some new ways of counting and introduce permutations and combinations. Then after all of that, we'll be ready to relate the ideas of probability to thermal physics. But for the next several class periods, we won't be talking about thermal physics. We'll be talking about gambling and playing cards, those sorts of things, because those are the ways of easily explaining the ideas. And that's really what the next slide says. So let's talk about origins. Probability was invented for gambling. There was a Frenchman named Chevalier de Mere, and he had found out that he could actually make money by offering even odds on throwing a single 6 in 4 rolls of a die. He made money doing that for a while, but eventually everybody realized that he was going to win in the long term. So he wanted to continue his business, so he tried a more complicated one. And he reasoned plausibly that betting on getting a single double 6 in 24 rolls of a pair of dice would be profitable. It turned out not to be. He slowly went bankrupt. But anyway, let's figure out the mathematics behind this. So the first thing is we need to adopt a useful mathematical device. We want to know the probability of getting a 1/6 in 4 rolls of a dice first, but the easier thing to calculate is what's the probability of getting no 6s on 4 rolls of a dice, because then each event is a similar event. So a die has 6 faces, so the probability of not getting a 6 on one roll is 5 out of 6. There's one way you get a 6, and the other ways you get a 1, a 2, a 3, a 4, or a 5. The rolls of the die are independent from each other and don't influence the next roll. So to get the net probability, all we have to do is multiply the probabilities of the individual events. So what I'm doing now here is writing what's the probability of getting no 6s, given that the die is a fair die. So it's 5 out of 6 for the first roll, 5 out of 6 for the second, all the way up to the fourth. We multiply those together, and we find that that probability is 625 out of 1296. We're actually interested in the opposite result. We're interested in what's the probability of getting 1/6 in 4th rows. So all we have to do is to say the probability of getting a 6 in 4th rows of a die is 1 minus the probability of not getting 6, because the two probabilities have to add up to a 1, because one event or the other happens. That's greater than half, and so we can see that the event would win you money if you made that bet. So we can summarize. The probability of getting a 6 with a fair die is 1 in 6 per throw, and the probability of not getting a 6 with a fair die is 5 out of 6 per throw. Now what I'm going to do is I'm going to introduce the idea of conditional probability. Note that I've written probabilities always as conditional probabilities. The little line in the middle of my probability statement can be read as given that. And one of the things that you need to know is there are actually two ways of looking at probability. There's what's called the frequentist, orthodox, or statistical school, which basically developed the idea of statistics to avoid calculating probabilities directly. And then there's the Bayesian or the Laplacian school. I'm a Bayesian, and the reason that I'm a Bayesian is I learned probability from a book by Harold Jeffreys, and it was the first probability book I'd come across. I didn't realize that there were two different ideas, but for a long time, the so-called frequentist method was more popular, but it has recently been shown. When I say recently, I mean probably 25 years ago at this point. It's recently been shown that if the Bayesian methods and the frequentist methods give different answers, the frequentist method is the one that's wrong. So the frequentist methods, though, are frequently easier to realize, but sometimes you have to use the Bayesian method. That's something we'll come across again later, but Bayesians always write probabilities as conditional probability events. Something that's going to be useful to us is the idea of a sample space. A sample space is simply a list of all possible outcomes of an experiment. And so what I've done here is I've written out the sample space for a pair of dice, and I've put in all of the possible outcomes and for throws. And the top row represents the first die, the bottom row represents the second die, and by writing them this way, I have all of the possible outcomes. And you can see that there are 36 possible outcomes, and for rolling the pair of dice, and only one of them corresponds to a double six. So what that means is the probability of getting a double six on one single roll of a pair of dice is 1 in 36. The probability of not getting a double six is 35 out of 36. Well, to figure out why Chevalier de Mere lost money, we have to work out the probabilities. So he said 24 rolls. So the way to make this calculation is to multiply all of the separate terms together until we've multiplied enough terms for 24. And to do that, just like in two probabilities, you multiply two numbers together to get the 24 rolls. We just have to take the probability for the individual throw and raise it to the power 24. And when you work that out, it's 0.5086. So it's no surprise that Chevalier de Mere lost money. This number is really close to a half, but when you subtract it from 1, it's going to be less than a half. So you can see why Chevalier de Mere lost money. Also, he might have tried this calculation, but it's so close to a half, he may have thought that he was coming out on the right side of a half. Turns out if he'd done 25 rolls instead of 24, then he'd have been okay, because the 25 would have taken you to the other side of the probability. But anyway, that's what went wrong with Chevalier de Mere's bet, but Laplace was motivated to develop the basic theories of probability by looking at gambling situations just like this one. Well, we haven't actually defined probability yet, so we had better do so. If there are several equally likely, mutually exclusive, and collectively exhaustive outcomes to an experiment, the probability of an event E is given by the probability that E occurs given that the conditions are, and then it's the number of outcomes favorable to E divided by the total number of outcomes. not every experiment can be broken down into equally likely events. For instance, what's the probability of snow on June 21st? So we can make this calculation by checking the number of successful occurrences of the event divided by the total number of trials. And if we take large numbers, this will approach the actual probability. I'm going to finish today by introducing some basic terms. And so the event not A means A doesn't happen. The event A or B means that in an experiment either A occurs or B occurs or both occur. The event A then B is if in successive experiments A occurs in the first and B occurs in the second, and we say that A and B are disjoint events if it's impossible for them to both occur simultaneously. And I guess we had better look at compounding probabilities because we will do that a lot. So if A and B are independent successive events or experiments, the probability of A then B is the probability of A multiplied by the probability of B. The probability of something not occurring is 1 minus the probability of it occurring. And if A and B are disjoint events, the probability of getting A or B in a trial is the probability of A occurring plus the probability of B occurring. Those are the rules that we'll use and apply to a variety of situations. But that's going to be what we're going to talk about in the synchronous session next Monday. So today I'm going to wind up and I just ask you to gain basic familiarity with the things that I've talked about. We'll be getting lots of practice. But I did want you to have it read at least this far so you can follow the examples next Monday. Have a good afternoon.